Hello CIO world, and welcome to another installment of piping system design. This is compressible flow. In this section, we will focus our attention on compressible flow. The conditions for compressible flow will be dealt with, and we will modify the mechanical energy balance somewhat to accommodate for the more complex nature of compressible flows. We will also define the Mach number, which is another dimensionless number that we like to use, and also the meanings of things like sonic flow, supersonic flow, subsonic flow, etc. And also understand what happens when you throttle flow or force flow through a smaller orifice. Something that you have probably come across before in mass transfer without knowing it when you deal with things like flash drums, etc. It is important to understand the steps as well as the assumptions that are used in the derivation of the two models that we will be using to describe compressible flows mathematically. This is because sometimes the process that you are analyzing does not have or does not apply to these assumptions, and so you can't use the equations. So just be sure on how these two models are derived so that you know when and where they are applicable. We should also know how to treat all the terms in the mechanical energy balance. When we deal with gases, we tend to deal with compressible flows. And so certain terms can be cancelled out and some will remain. We will also go over sonic flows that cause shock waves, as well as flow through nozzles, and how a converging nozzle can be used to measure flow rates. We should also understand why there exists maximum flow rates for a converging and diverging nozzle, and how these are defined mathematically. And last, we will also look at the limits in maximum flow rates through these devices. Now, first off, how does one define compressible flow? Flows are typically considered compressible when the density varies by more than 5 to 10%. In practice, compressible flows are normally limited to gases, supercritical fluids, and multi-phase flows which contain gases. Note, though, that liquid flows may also be compressible under certain conditions. In practice, it is not possible for us to measure density, but since density is a function of pressure, which is easily measured, we use pressure instead to define compressible flows. Right, so recall that the differences in the end pressures and pressure due to elevation will typically remain the same irrespective of the flow of the fluid, and therefore we do not have to consider in defining these so for the onset of compressible flow. So when do we deal with a compressible flow? Fortunately, we can neglect the endpoint pressures and the elevation. Instead, we only look at what is known as the subtotal variables, which has been introduced in the previous lecture. If the ratio of the change in these subtotal variable pressures and the upstream pressure P1 is less than 10%, then flow is typically assumed to be incompressible, or we could treat it as incompressible and apply our Darcy-Weisbach equations as need be. In other words, if the subtotal variable pressure is greater than 10% of the upstream pressure, then we are most definitely dealing with compressible flow and must take into account the drop in density that is likely to be occurring. Remember that subtotal variable pressures change and that they are the change in pressure due to equipment, friction, and also kinetic energy losses. Now, most situations tend to be polytropic in nature, and this increases the complexity of the calculations which we will need to do. A polytropic process is characterized by a relationship P times by V to the power of N is equal to a constant. Okay, so this multiplicity is constant. Fortunately, for isothermal and isentropic conditions, we take n equal to 1 and n equal to gamma, respectively. The handbook uses the symbol K instead, so don't be confused by the use of gamma here. This is just the more appropriate symbol to use, but the handbook has decided to use K instead. And these are the two main cases which we will be considering, the isothermal and isentropic cases, since they provide bounds for a range of real behavior, and in many cases the two models provide similar results for other types of flow cases that one would come across in practice. So just to be sure here, gamma is simply the ratio of the heat capacity at constant pressure over the heat capacity at constant volume, and in the handbook we use the symbol K for this instead. For the derivations, it is important to know the different properties being used and applied, which are summarized here as well as in the handbook for your perusal. So go over those and just see that you understand their meaning, such as specific volume. We assume that the ideal gas law holds, more or less. Obviously, this will simplify the equations that we will be deriving. And we'll also define density as such in terms of the ideal gas law. The departure point is to consider the polytropic situation where PV to the power of n is a constant. For isothermal processes, where delta T is equal to 0 and n is taken equal to 1, the derivation is slightly less complex. Well, for the adiabatic case, we take no heat being transferred through the pipe, and where this is irreversible, entropy is also taken to be a constant, and n is equal to k instead of 1. Also take note of how we define enthalpy as well as heat capacities in this case. We will go over the assumptions for these two models, but quickly you can just highlight or just make a note somewhere. On page 41, there are some useful relationships that are given to you in terms of how to calculate the universal gas constant R, for example, and also put the thermal, the specific heats in terms of K, the specific ratios, and R. Okay, so this is just an easy way to write these out. Now, you may have heard of something about the Mach number, perhaps in an advert or on a YouTube video. The Mach number is associated with sonic conditions, and it is a dimensionless number, just like Reynolds and Prandtl, etc. Now, the Mach number is defined as the ratio of the linear velocity of the fluid in question divided by the speed of sound through the same fluid. The sonic velocity may be determined by the square root of the specific heat ratio times by pressure and then divided by density. Note the units here and be sure not to make any careless mistakes, particularly pressure. That's why I prefer to write pressure in its energy form, joules per meter cube, rather than using Pascal or kilopascal, which really just complicates matters unnecessarily. Just to make sure, try to calculate the Mach number of air flowing at a rate of 100 meters per second using the following data. You can pause here now and try it yourself, and then move on and see if you can get the answer that I get. I measure the sonic velocity for this fluid at 331.1 meters per second, which is typical for air, and the Mach number in this case is 0.3. So we are well in subsonic flow conditions at this point. Flow that is below a Mach number of 1, as you heard me say now, is subsonic, whereas a flow that has reached a Mach number of 1 is said to be sonic, and any flow with a Mach number above 1 is said to be supersonic. The hedgehog. I said it. Moving on. Now that we have defined the most important concepts in compressible flows, let us go over this derivation quickly. It is given to you in the textbook, so just be sure to follow along and study it more in depth. I will probably skip over a lot of things, so if you're confused, just turn back to the handbook and go over the derivation yourself. So the derivation for the isothermal model will begin on page 41, and this is taken for long and uninsulated pipes. Now in this derivation, the following assumptions are made. Alpha EK is taken to be 1, which is for mostly turbulent flows. Obviously we in practice we tend not to use laminar flow. It's just too slow and uneconomic. Elevation in this case is negligible, simply because we are working with gases. And so this is a very reasonable assumption to be making. And also F is replaced in the equation by the Darcy-Weisbach equation. At normal pressures, the viscosity of a gas is only a function of the temperature, and therefore the Reynolds number as well as the friction factor can be treated as a constant in this case. And this is very useful in terms of calculating the friction factor. All right. But you can also remember that it is only so that we have one diameter that we can actually do the sort of calculation. If we have a different diameter, the following derivation will not apply. We will see later how sudden changes in diameters affect compressible flows, and so you'll understand why we don't tend to include reducers and enlargers. That being said, if you come across a change in diameter and you're doing a mechanical energy balance, you can simply just split your analysis at this junction where the diameter changes so that you have more terminal points, and the calculation then becomes more trivial in that regard. The adiabatic model is only applicable for shorter sections of pipe that are well insulated, or that the pipes are short enough that you can assume that the fluid is acting under adiabatic conditions. There should also be no fluid movers present in the energy balance. So if you see a fluid mover, then just split up the energy balance around this fluid mover. So as such, the change in enthalpy is equal to the change of kinetic energy, and you see the term split up here as shown. So in completing the derivation, we have a few variables we have defined previously that we'd like to use, and you may go over this derivation yourself in the handbook and see where substitutions are made in order to understand how we got to the equations. So be sure to also take note of the assumptions and conditions which need to be met for these derivations. So let us pause here for a moment and go over the summaries provided in the handbook. There is also a discussion on the application of these models a few pages on still, which we will cover shortly. Appendixes D1 and D2 summarize the two algorithms that are typically used with the isothermal case. D1 is used to determine the pressure drop going from P1 to P2, and generally we will know either P1 or P2 in this case, whereas the appendix D2 gives a method for determining the mass flow that is found by converging and testing the friction factor. Once the friction factor has converged, then you can use the resulting mass flow. The appendix D3 and D4 provide similar algorithms for determining the pressure drops as well as the mass flow rates, but tend to be a bit more involved as they typically require slightly more iteration. We'll go over this in due course. Now that we have the two models, we can discuss an important limitation in compressible flows regarding flow choking. Right, so as with any other sort of flow, we have a drop in pressure. Okay, so due to the conservation of mass in a pipe that is of constant volume or a constant diameter, rho times by velocity will remain constant. But rho decreases across the pipe because the pressure, the drop in pressure along the length of pipe also decreases, and so the velocity must increase. Now, since the pressure can never drop all the way to zero absolute, there is a phenomenon that occurs here instead, which is referred to as flow choking. So consider the example shown here. Note that although the speed of sound is higher in a less dense substance, as I've calculated here, the Mach number in any case would increase and increase gradually due to the pressure drop that is present. And eventually we will reach a sonic velocity where Mach number is equal to 1. Now, for changes in diameter, the conservation of mass must always hold true. And at the same time, the pressure that is being measured drops considerably at the reduced diameter as shown. So if we had to put in a manometer across the two diameters, then we would measure P2 as being smaller. But now, how can you explain this? I do give an explanation at the back of this lecture at the end, but you can consider the fluid moving more as particles that are bumping into the wall as well as themselves. The closer that you get to the throat section, the less they collide with each other and the more they tend to flow linearly through the throat. So it's got to do with their linear velocity and in which direction they are moving when they reach the throat. There is in fact much less restriction in the throat than behind the throat because of the way that the particles interact with the throat as they enter it and pass through it, such that the velocities will then speed up considerably. The density drops also as a result, and this gives rise to a drop in the pressure being measured here. But as I've said before, pressure can never drop all the way down to zero. And this is because there is a limit to how fast the particles can travel through the throat. Therefore, the fluid reaches a maximum velocity through the throat, and this happens or occurs when the throat is small enough, or the restriction is so small that you reach this maximum. It also has to do with the net sum of the forces over this control volume. Now, for isothermal flows, the maximum velocity occurs at a Mach number equal to 1 over the square root of K, which is the specific heat ratio, and also at 1 in the case of adiabatic flows. A figure on page 48 gives a relatively good summary of the trends that are expected for the pressure, velocity, and temperature, and you can go over these yourself. Note the differences in the two models with respect to the pressure drops, as well as the temperature drops and the velocity profiles. Now, as promised, the handbook provides an approach that may be taken when analyzing compressible flows. But remember to test for this by determining the subtotal variable pressure drop in relation to the upstream pressure P1. Since gases seldom have a density required to cause a significant pressure drop due to the elevation, we tend to neglect pressure differences due to elevation. Okay, obviously the atmosphere is quite tall or quite high up, and so just by the fact that there's all this height we actually have a significant pressure due to this height of the gas. But for all intents and purposes, in a chemical plant, unless the gas is really, really dense and under very high pressure, close to its critical point, we can then just neglect elevation. The endpoint pressures are used as is, and we determine the other variable pressure drops accordingly. It is sometimes necessary to use prorating when determining the pressure drops across equipment. The pressure drops caused by control valves, for instance, are discussed in a later chapter, so we won't deal with those at the moment. Now, the most complex part of the calculations comes in the determination of the pressure drop caused due to friction as well as kinetic energy losses, which are functions of the change in density themselves. And this change in density simply cannot be ignored in the case of compressible flows, and so we must account for this. On page 49, we are provided with a thorough discussion of how to go about accounting for this issue. Firstly, only consider one diameter at a time, since the equations do not accommodate changes in diameters. Secondly, evaluations must be completed incrementally for different pipe diameters. So therefore, only include fittings which do not reduce the cross-sectional area significantly, such as elbows and T's. Partly open valves, for instance, do not fit the bill in this case, and so you should split up your mechanical energy balance accordingly. The procedure is then approached as follows. You apply the mechanical energy balance as shown here, where delta P F prime K is equal to P1 minus P2, and either P1 or P2 would be known in this case. Then an analysis is completed from point I to point J, and the fluid exits the vessel and enters the pipe, and its entrance is then taken as this point I. By computing the mechanical energy balance, it can be shown that point I is equal to point 1 minus delta Pf prime minus delta Pke, kinetic energy, right? So confirm that the subtotal variable is now less than 10% of P1, which is usually the case in this instance, and then you can compute delta Pf prime and delta Pek for a compressible flow. Now delta Pek has to do with the fact that there's no flow in the tank 1, and then there is flow through the pipe, and so we can use the resistance coefficients accordingly to determine these two frictional losses. All right. Next, let's consider the mechanical energy balance across the length of pipe from point I to point J, and then check incompressible flow again and perform your computations accordingly, and just make sure of all the fittings that are located along the pipe, and split up the mechanical energy balance if necessary. Lastly, it can be shown that delta Pf prime equals the change in kinetic energy at the exit of the pipe, which makes sense since the flow arrests at point 2. But keep this in mind, these calculations should always be completed incrementally, since the density changes have to be accounted for in the case where we have compressible flow. All right, but of course if we do it incrementally, then we can approximate incompressible flow compressible flow with incompressible flow. Okay, now again, the appendices D3 and D4, for instance, provide useful algorithms for completing these calculations with respect to adiabatic flows, and then obviously for isothermal flows as well. But the adiabatic flows are, I think, the more tricky of the two. Compressible flows through nozzles have many important applications. Think about when you use a spray can filled with deodorant or filled with an aerosol that you want to vaporize. Right. It makes a lot of noise. Okay, so think about the noise that it creates. Also other applications, which include the action of the relief valves and burst discs that are used to relieve very high pressure safely when a pressure limit is exceeded. And these cause throttling so that you don't have too much flow rate going out of the highly pressurized vessel. And this is just for safety reasons as well, right? Now, because of the short distance across a nozzle, friction and heat transfer across a nozzle is assumed to be negligible, and we treat flow as adiabatic going through nozzles. If the derivation, in the derivation of the equations which explain flow through nozzles, it can be shown that by using the velocity relation that is given in equation 5.26, with the area of the throat taken into consideration here, the throat velocity is in terms of the Mach number and is a function of the pressure ratio P1 over P2. If the pressure differential is large enough between P1 and the final pressure, P2, or the back pressure, PB, we refer to the back pressure as being the final pressure. So this is maybe an ambient pressure of the atmosphere, right? So in any case, then we say that the sonic flow, which is caused because we reach a Mach number of 1, will occur inside the nozzle if this pressure differential between the upstream and the downstream pressures are substantial enough. Now, during subsonic flow conditions, P2 can sometimes equal the back pressure P1, PB, I mean, which is not a very high pressure. So Mach number tends to be maybe 0.3 to 0.7. While in the case where we actually reach sonic flows, P2 will be typically greater than the back pressure. It's not always the case, but usually it would be the case in terms of these sorts of converging nozzles. If we have a diverging nozzle connected to this, then this would not be the case, but we'll be discussing this in a bit later. So just take note of the equations 5.28 and 5.29 in the handbook, which show that P1 over P2 is greater than P2 critical over P1, since the Mach number is taken to be equal to 1 in this case. Now, another useful application for nozzles, and converging nozzles in particular, is in their ability to measure flow rate. It is done by using the equations that are shown here, and using these two equations with equation 5.28, we obtain the following result. Note that the terms on the right-hand side are only dependent on the properties of the gas in question. So by measuring temperature and pressure, for instance, the flow rate through the nozzle can be calculated, W max. I would suggest reading over the section again to make sure that you fully understand the implications of these results. One consequence of converging nozzles that might not have been clear on first glance or at first glance is that mass flow rate would increase with an increase in the upstream pressure P1, and under the same conditions velocities will remain sonic in this case. Okay, so this is why it is possible to measure the mass flow rate because the velocities remain sonic. The mass flow rate is a maximum and is still dependent on P1 and obviously T1 as well. Okay, so if we can measure all of these properties, or we know the properties of the fluid, then we'll be able to measure a flow rate through the nozzle. Okay, and obviously then back calculate the flow rate through the pipe diameter. Let's now look at diverging nozzles as shown here. The handbook discusses this in more detail on page 55 through to page 57. A gas that passes through a throat at subsonic flows will spread out as it approaches the throat, but the spread will be in the linear direction, parallel to the pipe. And then it will kind of slow down again as it exits the pipe. And it will act as a liquid would act in this case. There would be an increase in velocity through the neck or through the throat, and then out of the throat the velocity will decrease again. But when we are dealing with the case of sonic flows being reached inside the throat instead, the gas would accelerate as it approaches the throat and continue to expand as it enters the diverging section, leaving the throat. This causes the gas to accelerate, and it is then able to reach supersonic flow. This immediately makes us think of things like trumpets or rockets, for instance. And I mean, imagine what these sorts of things sound like. They're quite noisy. So, you know, when you start reaching sonic flows, it really sounds quite noisy. It makes this very, very sharp, almost like an aeroplane. So you'll definitely know when you've reached sonic flows in a pipe. Okay. Now, Figure 4 gives some further details by summarizing the pressure profiles. And also there's a discussion in terms of the velocity profile in section 5.9.1, which you should also go over in more depth. Obviously in this lecture we don't cover it so much in depth, I just summarize it for you. Now for the case of subsonic flows, the pressure profile looks something like shown here, where the pressure drops inside the throat and then increases due to the increased collisions of the particles as they are leaving the throat, and you know, the slower particles that they are bumping into kind of cause them to bump backwards as well. Now note, however, that the upstream pressure P1 is still larger than the back pressure PB further downstream, so that the overall or the net pressure drop across the section still causes the flow to be in the direction of the downstream pressure. As the back pressure is reduced, so this is PB, the pressure decrease causes a higher pressure gradient, but also the pressure difference between the upstream and the downstream pressure will cause higher velocities through the throat. And P3 will sort of approach the back pressure. So the pressures will drop more and more close to the throat, closer and closer to the throat. If the flow reaches sonic conditions, then the velocity inside the throat will reach a maximum value, and it will also cause some throttling, some noise to occur. Right. And if the back pressure is reduced even further, then a shock wave that is normal to the flow is produced, shown here in the yellow part. All right. A further reduction in the back pressure will move this shock wave downstream, and you can see this shown in the handbook. As such, it is possible to obtain supersonic flow through this type of nozzle. Now, can you think of any applications for such converging diverging nozzles? I think they're referred to as de Laval nozzles, after the French person that made them famous. Okay. Now, a question that you might have had sitting in the back of your mind for some time now is, why would the pressure in the throat decrease instead of increase? Because you're squeezing the flow, so surely pressure should be increasing. Now remember that the fluid is made up of particles, and it is these particles and their collisions, the collisions of these particles with the wall, for instance, that results in the pressure that we may measure at a macroscopic level. If the particles have a large enough velocity that is perpendicular to the walls of the pipe, then it is more likely to bounce back rather than enter the narrow section of the pipe. Whereas if a particle is more likely to have its velocity component or a large component of its velocity that is parallel to the pipe wall, then the particle is more likely to enter the narrow section of the pipe. And this is why the pressure in this case drops the way it does. Now that is the end of chapter 5 of piping system design. I hope you guys will have a good read of this chapter as well. It covers some very difficult material, so be sure not to just rely on this lecture. So hopefully see you soon, and in the next lecture on piping systems we will have a look at non-Newtonian flows. Goodbye for now.